All right, everyone. Thank you for coming in this week's Facts with SPAAM seminar. Our first speaker for today will be Phoebe, and she will be talking about estimating the strength of symptom propagation.
Thank you very much. So my name is Phoebe. Today I'm just going to be chatting about some of the recent work I've been getting up to in my PhD. So my whole PhD is looking at this concept of symptom propagation. So this is when the symptoms and individual experiences depends at least partially on the symptom severity of the person who infected them. So we've got kind of two scenarios, one mildly infected person in yellow and one severely infected person in red. So under symptom propagation, we would expect this mild person to cause more mild secondary infections and this severe person to cause more severe secondary infections. And the question of this specific bit of my research is, how can we tell if this is happening from data? So we're looking specifically here at synthetic data. So the main question here is trying to figure out what sort of data we need to answer this question. So before we start looking at some data, first we've got to think about how we can include symptom propagation in our models. So this is kind of the overall probability model. So we have two parameters here. We have an alpha and a nu. So the model set up so this alpha parameter completely controls the symptom propagation. So we call this the strength of symptom propagation. So with probability alpha, you always copy the symptom severity of the person who infected you. And then with probability 1 minus alpha, you revert to this kind of underlying baseline probability of severe disease. So if alpha equals 0, this kind of returns to the standard epidemiological two-severity model. And we've spoken about this more in other papers looking at the results when you include these two parameters in your models. So from this model of symptom severity, we need to first generate our synthetic data before we can do any inference. So we have these various rates for the various events that can happen in our system. So we've got 4 different possible infection events corresponding to the 4 different possible combinations of primary case and secondary case severity. And these probabilities correspond to the previous diagram. So if we look at the first row, the probability of going a mild person causing a mild secondary infection is alpha plus 1 minus alpha times the baseline probability of mild disease. And then this is the same for all of the other infection cases. And then we've also got 2 possible recovery events that can happen. So in this work, we use the tau-leaping algorithm. So the easiest way of doing this, and I guess most exact way of modeling this, would be to use the Gillespie algorithm, where basically each time step you have 1 possible event that can happen, and the probability of each event happening is just proportional to the rate. So you would add up all these rates, and then the probability of, say, infection from mild to mild would be this divided by the total rate. The tau-leaping algorithm is a kind of approximation of this, which we use because it's much, much faster. So what we do is we have a time step tau here equal to 1, so equal to 1 day in this model. We initialize all our compartments, so we start with 1 mild, 1 severe case and assume everyone else is susceptible. We calculate all our rates, which is what was in the previous table. And then for each possible event, we generate the number of times each event happens during this time step of 1 day. And this is just a Poisson distribution with rate parameter tau, our time step, multiplied by the rate for that event. And then we update all of our states, noting that sometimes you can end up with too many of each event happening, so you could have too many recoveries for the number of infections you have. So you have to do a bit of undoing there to make sure we don't have any negative people. And we just keep doing that until we have no more infected people. So this is much, much faster, especially when you're considering a large population. So here we have 100,000 people in our population. If you try to do the Gillespie algorithm, then at every step you only have at most one person being infected. or one person recovering. So you would just end up with a kind of ridiculous number of steps. But here we can just do a couple of very easy calculations at each time step. And then for our synthetic data, we output the number of each type of infection event at each time step. So at time 1, how many times was there a mild to mild infection event, mild to severe, etc. So, since, like I said earlier, the main question here is trying to figure out what type of data we need for this inference. We assume we have 2 independent data streams. So we have one overall population of synthetic data, and we can kind of pretend we have 2 independent groups of people doing 2 separate studies to collect data on this population. So the first one is we have some sort of contract tracing data. So we assume this is kind of aggregated, but it just means that we have information across the whole epidemic of how many of our infection events were of each type. And then we also assume we have some population incidence data. So this is just at each time step, what proportion of new cases are mild or, well, how many new cases are mild and how many new cases are severe. And these will be a sample of the overall population. So the population is 100,000 people, but we sample up to 10,000 of these cases. And yeah, so there'll be independent kind of subsets of the population considered in each of these. And the NCT will be our number of contact tracing data points, and the NP will be our number of population incidence data points. So from this data, the next step is to calculate our likelihoods. So the idea is we have a possible combination of alpha and nu. So alpha is the strength of symptom propagation, and nu is our baseline probability of severe disease. And we want to find out what's the likelihood of theta, which is this combination, given our data. So we're going to first look at the contract tracing data. So these are the total number of each of the different infection events, so mild to mild, mild to severe, etc. And this is directly proportionate to the probability of having these contact tracing data points given theta. So what we do here is we look at every possible combination of severity. So X is the severity of the primary case, and Y is the severity of the secondary case. And we just need to calculate the product of these to the power of how many times each event happens. So thinking back to the diagram we had before with our model for symptom propagation, this is exactly the same thing. So this is the probability of having mild disease given you're infected by someone with mild disease. Calculating the incidence, the likelihood from incidence data is a little bit more complicated. So what we need to know is, given theta, so given our potential combination of alpha and nu, we need to know what proportion of new cases will be severe at each time step. And this is something that we can't just write down analytically. So what we do is we use a modeled estimate for this proportion. So I've called it PT of theta. Yeah, and we can come up with this model estimate using an ODE model. So this is again based on the same model as before. The highlighted bits are the same probabilities before. These will come up again and again. But yeah, we can just run this model for our potential values of alpha and nu and come up with our PT of theta. So this is the likelihood for our incidence data. So the likelihood of theta, given this is a vector of the number of new mild cases at each time point, and then the same for the severe cases. Yeah, so we want to know the probability that we have these two numbers of new cases given our modeled estimate. And this can just be, this is just a binomial. So the probability of having this many severe cases given this many total cases, and this model estimate for the proportion of cases that should be severe at that time point for that value of theta. We consider, well, first we're going to consider just having contact tracing data and just having population incidence data, but then we're also going to consider having a combination. So we're assuming that everything is independent. Maybe don't think too hard about that. But yeah, we're assuming it's all independent so that we can just have our likelihood for theta given all of our data is just the product of our two separate likelihoods. And we're going to look at maximum likelihood estimates. So we look at the log likelihood just because it makes everyone's lives way, way easier, and take the value of theta that maximizes this, and then this theta hat will be our maximum likelihood estimate. Okay, some results. Oh no, my formatting. Okay, so here we have, along the columns, we have 3 different values of the number of contact tracing data points. And then each of these rows, we're looking at 2 different true values of alpha. So here's a very relatively small value of alpha, and then a bit of a stronger symptom propagation. And each of these, we're looking at 5 sort of replicate runs. So in each of these different runs, we'll sample this many data points from the same overall population synthetic data set. So this red dot is the true value, which we're trying to estimate, and then these green triangles are our maximum likelihood estimates for each of our runs, and the gray shaded regions are the 95% confidence regions for each of our runs. So if we first look at only having 10 contact tracing data points, somewhat unsurprisingly, we don't do a very good job of estimating our parameters. So our maximum likelihood estimates are about all over the place, but obviously 10 data points is maybe laughably small if someone was to do a study. We notice if we go up to 100 data points, we're getting more into the right region. So maybe not exactly on the red dot, but yeah, our maximum likelihood estimates, we're at least finding a relatively small amount of symptom propagation versus stronger symptom propagation. And then once we get up to 1,000 contact tracing data points, our estimates are even more accurate. So we're getting, even with 1,000 data points, which is still relatively small, we're getting pretty solid estimates, both for our alpha and our mu. Now, instead, we're going to look at just population instance data. So again, each of the columns is a different amount of data. This is slightly more than in the previous one. So yeah, 100, 1,000, and 10,000. So what we find here is, although our confidence regions do get narrower as we increase the amount of data, they get narrower along a sort of fixed line. So this line is the line on which the proportion of cases that are severe is fixed. So as you increase alpha, we expect more people to become severely infected because we assume that severe cases are more transmissible. And then also as you increase nu, well, this is basically, nu is just the severity. So as you increase that, cases will get more severe as well. So when we just have population incidence data, we can't actually really learn anything more about alpha. So you'll notice, especially looking at this row, even though our bands get narrower, looking just at how accurate our estimate is for alpha, it doesn't get that much better, even with 10,000 data points. So then we can look at having a combination of both. And now we get a bit of a best of both worlds. So this is all with 10,000 population incidence data points. Now we have this sort of narrow band, which we're pretty sure we lie upon. And then adding more contract tracing data means that we can kind of restrict in what our actual value of alpha is, so what the strength of symptom propagation actually is. So that was looking at the uncertainty across 5 replicates. This is now looking at 100 replicates, basically how good is our maximum likelihood estimate. So this is just, yeah, the error in the maximum likelihood estimate plotted looking at different numbers of contact tracing data points and then different numbers of population incidence data points. And you can see, looking here especially, our errors are pretty consistently small. So this is the median error and then the 95% confidence interval for the error. And then this is the errors in new, again, pretty similar. By the time we get to this point, everything's pretty good across basically all of our replicates. Okay. The last thing we wanted to look at was reporting bias. So there's a big issue in general data collection that severe cases are much more likely to be picked up than mild cases, especially when you have asymptomatic cases. This is kind of exacerbated because if a person doesn't even know they're infected, how are they going to tell other people that they're infected? Obviously, can be alleviated with robust testing measures, but that's a lot more expensive. So we assume in this scenario that there's only reporting bias in the contact tracing data. We assume the population incidence has been sort of adjusted for this, so that's giving us a good estimate for the actual proportion of cases that are severe. And we assume that severe cases are twice as likely to be detected as mild cases. And we have these 4 scenarios, so no reporting bias in only primary cases, reporting bias in only secondary cases, and reporting bias in both primary and secondary cases. So this is the same plot from before. So 100 replicates of each scenario, the median estimates. So we find that when we don't have any population incidence data, our estimate for alpha is actually still quite robust to these reporting biases. So especially at these lower values, lower true values of alpha, our median error is still saying low and our 95% interval, confidence interval is still pretty narrow. We find near the end, there's a bit of an increase in the error, but at this point, if it's a true value, alpha is 0.7, and you're estimating alpha is 0.8, that's not necessarily like the end of the world. Interestingly, when we add in population data, we find that in one of these scenarios, this is when we have reporting bias in both primary and secondary cases, we're actually increasing the error in alpha. And importantly, we're increasing the error in alpha for low values of alpha. So I'm sure you can imagine if the true value of alpha is 0, so there's no symptom propagation, and we're saying that we think it's 0.1, that's kind of much worse than if we're saying we think 0.7 is 0.8. And then we can also look at the errors in new, and we find kind of the opposite. So if you have no population incidence data, then you're going to be massively overestimating your new. But if you have population incidence data, that's kind of fixed. So we have this trade-off between do you care more about your estimate for alpha or your estimate for new, and how can we balance these 2 data streams to get the best possible result overall. And then just finally, one last plot. This is showing how often we detect symptom propagation. So this is what I was saying before about if you have the true value is alpha equals 0, and you predict alpha equals 1, then you're finding evidence for symptom propagation. There isn't actually any. So this is how many replicates do we find significant evidence for symptom propagation. So alpha equals 0 is not in the 95% confidence interval. So we expect to have much more support for symptom propagation as the true value of alpha increases, and that does happen. But this is kind of the interesting part. So for a true value of alpha equals 0 and reporting bias in both primary and secondary cases, in this case we find that there's significant support for symptom propagation in 80% of replicas. So we find evidence of symptom propagation in 80% of replicas, even though there wasn't any in the underlying data. So the point here is just to be really careful when you have reporting bias in contact tracing, but not population incidence, being really careful when you're putting those together. Here's just some quick conclusions. I think I've covered everything already. And then just some future work. Obviously, we'd like to do this with real data. And then also thinking about other data sets, so household data where you have correlations, people are more likely to infect each other, but we don't necessarily know if they have infected each other. And then also, can we estimate this reporting bias? That's everything. Thank you very much.